we should start this seminar. So today's speaker is Adam Bene. Adam is a physicist currently doing his PhD under supervision of Aram Harrow at MIT, and before that he did his undergrad at McGill University in Montreal. And Adam is Canadian, which I always find to be like a good feature in a person. So I'm very much looking forward to this talk. Thank you, Adam, for waking up so early and joining us.
Yeah, thanks, David, for the introduction. Let me I have an hour to talk. Is that correct?
Usually it's a bit shorter than that.
Oh, that's good, because this talk's a little shorter.
Yeah, so if you aim for a bit shorter so that we could have it within an hour with all the questions and stuff like that.
All right. Sounds good. All right, yeah. Hi, everybody. Thanks for coming. I guess a couple disclaimers. First is that it's still early over here. So if I say something, and waking up and having my tea, but if I say something that sounds silly, it's possible I've made a mistake. So I'm not sure the best way in this format to ping me, but I guess just ask a question afterwards. It's entirely possible. But all right, glad you all came. Sorry, just getting my face showing. All right, so yeah, this talk, it's joint work with Aram, Harrow, and Nicole Halpern. And it's also greatly helped by Chris McNally and John Wright. And among helpful discussions, something else that John Wright did is he gave the correct description of this talk, which is or this work when we were talking about it, and he described it as a fun lark, which is I think really exactly the right way to think about this project. Sort of just a sort of fun romp through hypotheticals and talking about these ideas of testing for entanglement in macroscopic systems. So we'll get started. This work was really motivated by a practical question, which is to say, let's say that you have some system, some wet squishy organ or some strange glowing test tube or a lump of metal, and for whatever reason, you think that maybe this system has some quantum mechanical effects going on. And you'd like to test for that. You'd like to, somehow investigate this macroscopic large system and say, is there something quantum mechanical happening? And if you want to do that, maybe the first question that you have to ask yourself is, before you even ask, is this experimentally possible? You have to say, is this even theoretically possible? Is there any way, just by taking a macroscopic system and making measurements of that macroscopic system, that you can detect quantum mechanical effects? Okay, so that's a question. Now that I've asked this question, there's really two more that we need to ask. First is what exactly do you mean detect quantum mechanical effects? And the second, well, it's what exactly do you mean by measuring a macroscopic system? Right, so define your terms. And so most of my talk is actually going to be about answering these two questions, getting our definitions in place, and then we'll finally move on to this question here and see that the answer is yes. Okay. So, but I'll start with the second question, which is this, what does it mean to measure a macroscopic system? What does it mean to be a macroscopic system? There's a simple answer, right? Say a macroscopic system is one that's big, macroscopically large. There's practically probably that's almost the right definition. But from a theory standpoint, with these quantum foundations things, you want to be a little there's reasons to be a little more careful, because throwing away any pretense of being an experimentally minded person, a macroscopic system, 1,000 qubits, 1,000,000 qubits, or 1 qubit sort of behaves the same way to me. I can imagine a 1,000 qubit GHZ state, which displays all the same features of entanglement as a 1 qubit GHZ state. And now, of course, there's lots of practical problems like decoherence, but from a far off sort of removed theoretical standpoint, just asking about what's possible, if all I care about is that my system has a lot of qubits, well, then of course, I can still see entanglement and do quantum mechanical things with it. So what we're after here is a definition that sort of forces a system by being macroscopic to appear a classical. We're sort of trying to give a definition that ties our hands behind our back a little bit. And hopefully, you know, such a definition makes the theory a little harder and a little more interesting, but also gives us a system that's more suitable for experiment. So this is supposed to be both sort of a theoretical tool and a description of a family of systems that are macroscopically large and sort of easier to prepare experimentally than a million qubit GHZ state. All right, so what's the definition? Well, let's start just with an arbitrary microscopic system. So here we have the full power of quantum mechanics. I have a few qubits. I can put them in absolutely any state that I want. And in particular, you know, they can be entangled with each other in whatever way that I want. Okay, so that's my microscopic system. Now, to make my macroscopic system, what am I going to do? Well, I'm just going to take n copies of the microscopic system, where n is some very, very large number, you know, on the order of Avogadro's number. So I've taken a microscopic system in any state that I want. And to make a macroscopic system, well, I'm just going to take n copies of my microscopic system. And critically, these are going to be n independent copies. So this forbids me from having something, you know, any sort of globally entangled state, because I have complete freedom in the microscopic systems, and then I just have to copy paste, you know, many, many, many times to get my macroscopic system. So that's a macroscopic system that's sort of interesting. I mean, it's more restricted than, there's some restrictions at least. And then the last thing we need to do is talk about what it means to measure this system. And well, there's a definition that's sort of natural now. To make a measurement of this system, what do? Well, I just define some measurement operator on the microscopic system that I started with. And then to measure the macroscopic system, well, I just apply the measurement operator to every one of my microscopic systems and sum up the response. So, you know, I have some 0-1 outcome measurement that I can make on a microscopic system. My macroscopic system just applies that 0-1 measurement to all of the microscopic systems and sums up what I see. So I'll get a number between, you know, 0 and n. And that's almost good enough, but not quite, because if I could see that number exactly, I'd still have a lot of precision. You know, I'd still be able to talk about just what a single microscopic system is doing by ignoring all of the outcomes except for one. So let's just build in some uncertainty and say that my macroscopic measurement, well, it measures all of these microscopic systems, it sums up the responses, and then I only get to see that number with uncertainty square root n, just to stop me from being able to do something too finicky, where I just change a single one of the microscopic systems and can detect that. Okay, so that's the picture of a macroscopic system, and that's a general picture. For this talk, we're going to use the same framework, but I'm going to define something a little more specific. Remember, we started with a microscopic system, took n independent copies. Well, the microscopic system that I'm going to use for this talk, there's only one. I'm going to imagine a 2-qubit system in a Bell state. So there's my microscopic system. And I'm going to, for those of you who know, we're going to work towards a Bell test. You don't know what that means, we'll get to it by the end of the talk. But you know, just to start getting there, I'm going to take my microscopic system, 2 qubits in a Bell state, and I'm going to assume some space-like separation between them. So they're just 2 qubits that are somehow removed from each other, can't talk to each other. Okay, and now my prescription for getting from the microscopic system to the macroscopic system has been defined. I just take this microscopic system, and then I take n copies of it. So I go from 2 qubits in a singlet state to 2, I'm going to call them beams of qubits in a singlet state. And the cartoon that's almost right, unless you think about lasers a lot, in which case it's not, is to say that my macroscopic system, you know, you can think of just two laser beams consisting of lots of photons. And in each laser beam, one photon in one beam is in a Bell state with a photon in the other beam. I guess each photon in this first beam is in a Bell state with some photon in the other beam. And so that's my macroscopic system. And okay, then what's my measurement? Well, oh, whoops. Sorry, everybody. Let me just keep on. I was trying to get a clock at the same time, but I don't think I can do that. So we'll just go with this. Okay, my macroscopic system is two beams of photons, pairwise in these singlet states. And then my measurement, well, my measurement just looks like applying some rotation to one of the photons in one beam, and then measuring an intensity. Or you could think of passing the photons in the beam through a polarizer and then measuring the intensity of the resulting beam. Because that's exactly what we defined before, right? When I measure the intensity, I'm just counting the total number of photons in a certain state. And then there's some built-in measurement error, which is what we wanted. So hopefully that picture is clear to people. That's sort of our setup. And now we're going to take this system and start moving towards our second question of now, can I somehow make measurements of the system that reveal entanglement? Well, let's make some basic observations. And the first is that, well, can we see entanglement? Can we see quantum mechanics at all? Like, has quantum mechanics just disappeared from the system completely? And the answer is no. I mean, I can see quantum mechanics. Quantum mechanics has not disappeared. And the little cartoon that I have that shows that is to imagine now just one beam of photons. And imagine, one beam of n photons, and imagine just measuring the intensity of the photons in that beam. And now I've drawn the intensity here with a little bit of a squiggle. Maybe the way that I've set it up, you should imagine your intensity measurement is just constant. I just see, exactly n photons. I guess the little squiggle comes from my potential measurement error. But that's our start. And now I take this beam of photons and I pass it through a polarizer at 45 degrees. Well, what's going to happen? One thing that we know is going to happen is that the intensity is going to drop off. I'll go from seeing n to about n over 2 photons. But the other thing that's sort of interesting is that this up here was just a straight line, or had very small uncertainty. When I pass through the polarizer, the uncertainty in my measurements gets bigger. If I guess this graph doesn't quite make sense, right? You should imagine this is making a bunch of different measurements or something. I mean, I can't measure the same beam twice, but I redo the experiment and measure at a different point in time if you want. I could even measure at the same point in time. But the uncertainty in my measurement after passing through this polarizer gets larger. And why is that? Well, every time a photon passes through this polarizer, there's a coin flip. It either passes through or it doesn't. It happens with 50% probability. And so if up here I had exactly n photons, no matter what, here I have really, truly a random number of photons, with uncertainty on the order square root n. So that's our first observation, just to see that quantum mechanics somehow at least shows up in our measurements, right? Because this passing through the polarizer is random for quantum mechanical reasons. Okay, and we can say something a little more sophisticated than that. Remember, we had two beams of photons, and the photons were in an entangled state. And you could say that, well, if these systems are entangled, then the randomness is correlated. It's not just that. Well, yeah, you have this randomness that's purely quantum mechanical, and you can see correlations in this randomness, right? If my photon passes through this polarizer, it's in the up state. It's entangled with a photon over here that is in the up state. And so if lots of my photons passing through here, if a higher than average number of photons pass through here, a higher than average number of photons over here are in the up state, well, then a higher than average number of photons over here are in the up state as well. So, I have this uncertainty that's quantum mechanical, and it's correlated between two measurements separated in space. Okay, so that's kind of nice. You know, we have a quantum mechanical effect. We have something sort of non-trivial, which is this correlation between two different measurements. Question you ask, right, is this enough to detect entanglement? You know, I do this experiment, I see correlated randomness. Am I done now? Can I go home? And well, no. You know, there's the answer is no, and for a good reason. You know, you would see the same correlations even if your system was just classically correlated. You know, or another way to say it is even if your system decohered from being, you know, 1 over square root 2 up, up plus down, down, the singlet state, to just being a mixture of pairs of photons that are either up, up or down, down, just a classical mixture, you'd observe exactly the same correlations in your measurements. The same effect of, you know, of the randomness between your two different measurements being correlated would happen. So, you know, we see an effect that we can explain via quantum mechanics, but just seeing this effect and having that explanation isn't enough for us to conclude, you know, isn't enough for us to prove quantum mechanics. We can't just, you know, clap our hands and go home. Okay, so that's what I just said in words, but now in text. I'll give you a sec to read it, but it's not that different. Okay, so next question is, can we do better? You know, we have a test with outcomes that can be explained by entanglement, but does there exist a test that forces entanglement? It really doesn't give us any option other than to have produced the outcomes by measuring an entangled state. Well, in the microscopic case, the answer is yes. It's well known. It's the Bell test, and I'm going to say a little bit about that now. So put the macroscopic picture on pause for a sec. We'll come back to it, and let's just talk about Bell for a second. Okay. So, what is the Bell test? Bell's theorem? Well, it's proposed by John Bell, 1964. And now the first time I gave this talk, I was giving it to a very experimentally minded audience, and I wanted to say something to convince them that it was important. So if you ever find yourself in a similar situation, here's a good quote. It has been called, the Bell test, the most profound theorem in the history of science, which is, you know, perhaps slight overkill, but only slight. I mean, it's important. And I'm not actually going to talk about the Bell test so much. I'm going to talk about the refined version of it in sort of modern language, where you think of the Bell test as this thing called a non-local game, and in particular, the CHSH game, after the people who gave this refined description of it. Okay, so that's the plan. We're going to talk about CHSH for a little bit, and then we're going to generalize back to the macroscopic case. So, okay. What's the CHSH game? How does it work? Well, I've got two, we call them players, two parties that may or may not share entanglement. And I'm going to separate them so they can't communicate with each other. Now, I'm going to send Alice, this is Alice, this is Bob. I'm going to send Alice and Bob one of two possible questions. They're going to respond to their questions with a single bit response. So their question is either a 0 or a 1. Their response is either a 0 or a 1. And then just a word on notation. We're going to see a lot now these a sub I, b sub j variables. And the right way to read those is as AI is Alice's response to question I. BJ is Bob's response to question J. Just you know, we're gonna lose the picture in a little bit and just keep the variables AI and BJ. So it's important to have a dictionary in your head for reading those. Okay, but I have these two players. They're separated. I send them questions. They send me responses. And the last thing that we need to note is that, you know, Alice and Bob have some strategy for turning questions into responses. And in general, in generality, these strategies could be random, and so their responses are random variables. AI and BJ are random variables. And now these strategies that Alice and Bob use, well, they could be classical. Alice and Bob could just be flipping coins or just using a lookup table to decide what to say. Or they could be, quantum mechanical, where Alice measures a state and Bob measures a state and somehow uses the outcome of that state to decide her response. Okay, and now what does Bell's theorem tell us? It tells us that if Alice and Bob are classical, so if they're just using randomness, well, actually it turns out randomness doesn't help them, and you can define this quantity, that just this sum of different random variables multiplied together, and no matter what strategy Alice and Bob use, this quantity is upper bounded by 2. Right? This is the classical bound on Alice and Bob's ability to play the CHSH game. Okay, so that's nice. We've bounded what any classical party can do. And then the next thing you do is you show that, well, quantum mechanically, you can do better. So if Alice and Bob share a singlet state, and they make the right measurements and use those measurements to decide their outcomes, well, you define the same quantity, A0 and B0. The AIs and the BJs are just classical random variables. We decide them by measuring some quantum state, but AIs and BJs are just bits. And well, if these bits come from measurements of a quantum state, you can do better. Alice and Bob can do better than they could have done classically. Oh, okay. So what's the point of all of that? Well, this gives you a test, right? You want to see whether or not Alice and Bob share entanglement. You just make them play the CHSH game. You collect their responses. From their responses, you can figure out, you can estimate that parameter, that sum of expected values of AIs and BJs. And if you find that their responses violate the Bell bound, that 2, well, you know that they shared a quantum state. And now, of course, there's some disclaimers, which you can read while I talk, but it amounts to saying, well, this works. This is a test. It proves that they have a quantum state, and you're only as sure that they have a quantum state as you are sure that they followed the rules of the game, which said that they couldn't communicate with each other, said that the questions that you sent them were random. They didn't. When you sent Alice a question, she didn't know the question that Bob got. Stuff like this. But sort of at a high level, if you're certain, you know that Alice and Bob share a quantum state with exactly as much certainty as you had that they followed the rules of this game as defined, which you can be pretty certain of. I don't want to get too far into the weeds here, but hopefully that sounds okay. Okay. So that was the Bell test. And we just did it for a microscopic system. We just showed that if we forgot about this macroscopic system and macroscopic measurements requirement, then we could do a test that proved that my 2 systems shared entanglement, not just correlations. And now what we'd really like to do is take that test and upgrade it to the macroscopic setting. We'd like to be able to now have a macroscopic system and macroscopic measurements, and after interacting with it for some amount of time, conclude that the system had to be entangled. And so there's just a doodle reminding you of what the system looks like. While we do this, I'm just going to check the time again to see how I'm going. Okay, I think we're still on track. Okay, so there's my little doodle of our macroscopic system. We had, I guess you've hopefully read it in this time. We had 2 beams of singlets and independent singlets. Okay, and so with this macroscopic system now, we want to redo something like the Bell test. And we're going to get something that works. I mean, you can do something like the Bell test. That's the punchline of this talk. But before we get there, I want to show you something that doesn't quite work. And so the first thing that you might try and do that's ultimately not going to work is you could say, well, what if I just try and reproduce the microscopic Bell test, exactly. Okay, how would you do that? Well, you wanna imagine sending the players questions, and based on the question that each player gets, they're going to choose to measure their beams in one of two different bases. So this is how the microscopic Bell test works as well. If you send Alice a 0, she orients her polarizer one way. If you send her a 1, she orients her polarizer another way. Now, microscopically, they would just be measuring a single photon. Macroscopically, well, they can measure these beams. So they can make these macroscopic measurements and count the total number of photons they see when their polarizer is oriented either, polarizer is in one of two orientations. And then we can describe these macroscopic outcomes, A0, A1, B0, B1, that behave sort of exactly like the microscopic ones would. Now, there's one little, it's not a big deal, it's just a normalization, but, in the microscopic case, the Alice and Bob's responses were binary. They were just 0 or 1. Here, we're getting numbers between 0 and n, but we can just rescale those. So just divide out by your factor of n on the A and on the B. And well, you get a bound that looks just like Bell's bound and applies to any classical system. So, now A0, B0, A1, B1, those are random variables. I've divided out by an n, so they're random variables taking a value between 0 and 1. And if the system's classical, it turns out Bell's bound just works, So I have, in the macroscopic case, just like in the microscopic case, a bound on how well I can do classically. I have this quantity right here, and for any classical system I want, Alice and Bob can't exceed this quantity. Okay. And so that was the first half of the Bell test. We have a bound. Second half now is I want to show that there's some strategy, some measurements that I can make on quantum states that will exceed this bound. Right? And now our hands are tied behind our back. We can only make macroscopic measurements. And that presents a problem. Because the strategy that beat the Bell test bound, the strategy that got us to 2√2 involves sort of microscopic measurements on a single qubit. And we can't do that. All we can do is make these large collective measurements on a macroscopic number of qubits. But we can, we can define whatever macroscopic measurement we want. So just to see exactly why this fails, let's just try and duplicate the microscopic strategy. So let's say Alice and Bob set their polarizers exactly as they would to violate the microscopic Bell test. But now instead of measuring a single qubit, they measure n. All right. So that's what I'm saying right here. You set up your polarizers so that in the microscopic case, if you just looked at one singlet, you would beat the Bell bound. Okay, now what happens when you measure the macroscopic random variables? Well, I've just given you the answer here, but it's not too hard to see. This macroscopic random variable A0, it's a sum of a bunch of microscopic random variables that turn out to just be coin flips. They're 50-50 on their own. So, this thing comes out to be just n/2 by the law of large numbers with high probability. All of these things, the A0, the B0, the A1, the B1, they're all just coming out to be n/2. So when you take this huge quantity, divide out by the n squared, what do you get? You just get a half, which, isn't good. Our bound was 2. We wanted to beat 2√2. And so somehow just taking this microscopic system and straight away porting it over to the macroscopic case didn't work for us. There's sort of a way to see why, which is to say that Remember when we started, we said the quantum mechanical effect, the sort of thing that we cared about, was in the fluctuations and in the correlations in the fluctuations. So, the quantum mechanics here, the effect of this entanglement doesn't show up in the means of our macroscopic random variables, in the mean outcomes, which is what this thing is looking at. But it shows up in the variance. So sort of the first order moments don't see the quantum mechanical effects. The second order moments do, but when I take this, I'm dividing out by an n squared, which is gonna squash any sort of effects, any second order effects that I have in the means of these guys. And that's a little hand wavy. I say it because it's gonna motivate what I'm gonna show you next, which is a way to actually recover something functionally very close to a Bell test in this macroscopic case. Okay, so how do we do that? Well, we need another piece of theory, and that theory comes from this thing called the covariance Bell inequality, proved fairly recently. And so just as a reminder, here's what the Bell CHSH inequality looked like. These things were random variables, upper bounded by 2. And because they're random variables, I can find any quantity that I want. And the covariance Bell inequality gives me this statement instead. So, I'm not taking, I guess it's a similar looking statement, but I'm not taking the expected value of products. I'm taking the covariance between these pairs of random variables. There should be commas everywhere here, but I'm taking covariances between the A's and the B's. And I get an upper bound. It's not 2, but still pretty close, 16/7. Okay, and what's that good for? Why is that nice? Well, it turns out that just like you can violate the regular Bell CHSH inequality, you can also violate this covariance Bell inequality. So it's actually the same strategy even that violates this guy, gives you 2√2 when you compute this quantity, will give you 2√2 when you compute this quantity. And don't worry too much about these factors of 4 here. That's just they're conversion factors that show up when you switch between variables that have outcomes 1 and -1 and outcomes 0 and 1. So, if you're wondering why these 4s are sitting around, that's why. But okay, so we have this thing, covariance Bell inequality, and we have a quantum violation of it. So we've just got another microscopic Bell inequality that we could have checked. Okay, but now let's take this thing that sort of explicitly looks at second order moments and try and use that in the macroscopic case. Okay, so just like before, we take these macroscopic random variables, the outcomes of these macroscopic measurements, I guess macroscopic random variables that describe the outcomes of these macroscopic measurements. And we can write them as sums of microscopic random variables. And I think I just clicked through this earlier, so if you were listening to me talk, maybe you didn't see it. The superscript, this A1 alpha, the superscript alpha refers, we're in the macroscopic setting now, and we're talking about the measurement on the alpha singlet state. So there's n of these total. I sum up all of those measurements to get my macroscopic measurement. And this is like a single microscopic measurement. Okay, and now all we need is a tiny fact about covariance, which is to say that if I have 2 random variables, they're independent of each other, and I take the covariance of their sum, that's just the sum of their covariances. So, the covariance between this macroscopic A0 and B0, what is it? Well, it's just 4 times the covariance between the sum over, sorry, forget that 4. This is the first case of me waking up. I have this covariance between the macroscopic random variables, A0 and B0. What is that covariance? Well, it's just the sum of the covariances between the microscopic random variables. And now the microscopic random variables are independent everything except for their singlet pair. So so this covariance right here, this covariance between these two macroscopic random variables, I can get it just by summing the covariances between all the pairs of microscopic random variables. If that explanation confused you, you can check up yourself with less confusion than it'll take to unentangle that explanation just by remembering this fact. That if you have a sum of independent random variables, the covariance of the sum is the sum of the covariances. And that's all I've used here. And what I've done now is I've produced a bound that looks a lot like the microscopic bound, like this microscopic covariance Bell inequality, but it now bounds these macroscopic quantities. So this is still just our classical bound, but notice, I guess I could have divided out by n and normalized like before, but notice that now instead of normalizing by a factor of n squared, I'd only have to normalize by a factor of n. So exactly this fact that most of my covariances vanished between pairs of particles let me save a factor of n in my normalization, which is one way to look at this. The other way is to say that I took the microscopic bound and scaled it up to a sum of n microscopic systems. And so, of course, I just pulled out a factor of n in front. Either way, this is our now classical macroscopic covariance bound. And what do we want to do? We want to produce a quantum strategy that exceeds it. But that's easy because the sum of the covariance is the covariance. The covariance of the sum is the sum of the covariances. So if I just play with a microscopic quantum strategy that exceeds the bound, so if these microscopic random variables gave me 2√2, and I take the sum of the macroscopic, I take the covariance of the macroscopic random variables, I'm just going to add up the covariances of all of the microscopic random variables. That covariance was 2√2, so we're now playing with the quantum case. There's n of these in total, and so I see 2√2n. And that's really it. Looking at first order moments, we saw that sort of my quantum effects vanish. I normalized out by this n squared. All of my little wiggles just disappeared in the wash. But if I am willing to go to second order moments, look at covariances, well, then we can prove a bound, a classical bound, and we can show that these quantum fluctuations, produce a signal that exceeds it and gives us really a proof of quantum mechanics, a proof that entanglement is present in our system. So hopefully you're happy with that. That's our punchline. Oh yeah, sorry. I guess this is our punchline. 2√2 is bigger than 16/7, which you should check. But once you've noticed that, then you're really done. We've got a quantum strategy that just beats our classical bound. And so we have a signal that proves entanglement in a macroscopic system. Okay. So there's the conclusion, same thing in words, just one more time if you want to see it. Right. And that would be the end of it, except for I feel like I should give some honest disclaimers. I'm sorry, I'm just going to peek at the time one more time. Yeah, okay. I'll quickly give some honest disclaimers, and then hopefully we can have a discussion in which we can talk more about the disclaimers, which are maybe the most interesting part. So remember, in the regular Bell test, I said, well, you can conclude that the system is entangled. You can conclude that the system is entangled as long as you know that Alice and Bob followed the rules of the game. And in the microscopic Bell test case, those rules were pretty simple. We just had to make sure that Alice and Bob didn't talk to each other and that their questions were sort of evenly and randomly generated. Now, in the macroscopic Bell test case, we've got all of the same rules, but one extra one, which is that we required this independence of the microscopic systems. So remember, we turn that covariance of sums into sums of covariances by saying that that all of our microscopic systems were independent, except for the pairs that were entangled. And so that, that is at its heart, I guess, an experimental assumption. That's not something that you can necessarily force, because if Alice is holding a big bucket of microscopic systems, we can't know for sure that she hasn't sort of secretly correlated with them with each other when we weren't looking. So this test is reliant on sort of an experimental assumption in a way that the Bell's original test was not. And I guess I'm going to skip this note here, which is just something else you might worry about. I'll deal with it very quickly, was that I sort of stopped talking about that measurement uncertainty, that little square root n uncertainty in our measurement outcomes. Okay, I can talk about this more because it's sort of right. So this test is reliant on this experimental assumption. And I guess one thing that you could say, sorry, I forgot exactly what I had in this slide, but I can talk about it. It's reliant on this experimental assumption. And now one thing that you could say to make yourself feel a little bit better about having this experimental assumption is you could ask, well, how much correlation can Alice put in before she breaks the test? And the answer is, well, we're at least a little robust, and there's sort of a way of formalizing it, but if Alice correlates just a few of her random variables with each other, or correlates just a small number of her random variables very much, or just has loose correlations, well, the test is robust, and so, a small correlation only produces a small difference in our classical bound, and so you can absorb some amount of correlation. You can, I guess, expand your assumptions to allow for some amount of correlation and still get a useful macroscopic Bell test. And this is also important because remember at the very beginning, I said that you have this measurement error, this square root n uncertainty in each of your measurements. And if you're being really pessimistic, you could worry that measurement error was secretly correlated in a way that was helping Alice and Bob violate this test. And so, you can absorb sort of error on that order of magnitude at least, and still get a good test of entanglement. Yeah, and I'm going to skip this note. Yeah, maybe in the interest of not talking for too long and letting us instead have a discussion, I'm going to just say a tiny bit about these last points. Sorry, apologies. I'll skip these slides and I'll just tell you the punchline, which is to say, maybe, especially since this was billed as a quantum foundations talk, maybe the one sort of most important question you should ask is, okay, so you have this nice test that detects entanglement. What can it tell us, about quantum theory? Can these sort of macroscopic measurements do the same thing that the Bell test did in terms of just ruling out local hidden variable explanations for what was going on? And the answer, which I was sort of saying before, is that, well, almost, but you can only rule out local hidden variable explanations if you know that all of Alice's and all of Bob's subsystems were independent. And, there's sort of, you can do that with some experimental certainty, but you could always worry that there's some other sneaky way that Alice and Bob managed to correlate their systems, and sort of one that you'll never be able to get rid of with this sort of test. One possibility for correlations that this test just can't do anything about is that in order to notice a violation of this inequality, you're going to have to make measurements at many different times. You're going to have to repeatedly measure these A's and these B's. And so even if you watch Alice and Bob very closely, even if you see everything they've done, well, one thing that you could always worry about is that physics somehow was correlated with the time at which the measurements were made. And then each of these microscopic measurements would be correlated with the time in which they are made, meaning the measurements made at the same time share some correlation. And then this is sort of a loophole that this test can't deal with, can't get around, which is that, at least things being correlated with each other just because of the fact they're happening at the same instance in time will always give sort of a sneaky way to trick entanglement, to pretend like you have entanglement, at least for this test at the macroscopic scale. Okay. And I guess another way to say the same thing is to say that this test is nonlinear. So it's sort of, it can't be violated by a single classical distribution, but if you have a mixture of classical distributions at different points in time, then you can produce outcomes which appear to violate this test. Sort of just another way of saying what I just already said. Okay, so just quick summary. We have this macroscopic Bell test. It's great. What can it do? Well, you can have a reasonably convincing test of entanglement in these sort of macroscopic systems with macroscopic measurements where you have imperfect control of what's going on. And hopefully also it lets you sort of construct easier Bell tests than you would microscopically, because these macroscopic systems are sort of easier to generate and measure. And it also sort of gives this sort of picture, some clarity on what macroscopic entanglement is worth, where at least in this example, you see this sort of trade-off between macroscopic entanglement and global correlation, where either of them could simulate the other. All right, and now what can't this test do? Just an important note, you can't rule out local hidden variable theories. So in that sense, at least, Bell does something that we can't. Okay, and I've got a couple experimental slides, which I don't think I'm going to go into, except for maybe in discussion. So I think I will stop there, having run for 50 minutes, and just open this up for discussion, I guess. But thanks, everyone.
Thanks a lot, Adam. That was a great talk. I'm a big fan of having PhD students give talks, because then you can actually understand and follow them. This was really interesting. I should say to everyone listening, like if, as I said in the beginning, if you have a question, just press the Q&A button and say, hey, I want to ask a question. And meanwhile you do that, I thought I'd ask a question, but you might have answered it in these last slides where you mentioned this global correlations and stuff like this. Yeah. My question was like, so, I mean, this kind of setup, you could use on the microscopic level, you could use this for like device independent key distribution or something like this. And you could have Alice and Bob, instead of violating a Bell inequality, they're building a secret key that they could use to communicate. And then
yes,
I thought, could you extend this framework of yours into a system where you could like distill a secret key for Alice and Bob? So like you assume that, okay, quantum mechanics is okay and there is no local hidden variable theory, and you trust this party that creates the two beams. Is there then a way, I guess my question is there a way for Eve to interfere with the two separate beams and put in this global so that you can't do this?
That's a really interesting question. I don't know, but I'll speculate. So I think one attack that should always be available to Eve, because of this global correlations, is if she could somehow collect all of the qubits, collect both of these beams, measure them all, and send back beams that are where the photons are somehow all correlated with each other. I think just because that's sort of a sort of universal weakness of this, I think such an attack should work. But if you maintain this independence requirement that the photons in one beam are all pairwise independent of each other, and somehow say that Eve doesn't have the capability to do that, she can't muck around with this independence, then you'd want something like rigidity, which is this property that says that if if you're close to optimum, you know what the measurements are close to, and and I don't know if that holds, but it's possible that it does. So actually, maybe rigidity isn't quite right, but anyways, it's possible that you could do something like that, conditioned on Eve not being able to muck around with this independence requirement. That would be my speculation. It's sort of an interesting question.
Yeah, I mean, I guess if the answer to the question is that you can do something useful with it, then that's potentially.
Yeah. I guess maybe one thing to say is that one way of rephrasing this covariance test that works, I'm trying to remember the details, is you could imagine sort of a binary measurement where you just check whether every time Alice makes a measurement, she checks whether the number of outcomes she has observed is bigger or less than the mean number. And let's say, if it's very close to the mean, if it's within error of the mean, she ignores it. If she sees much more than n/2 systems, she calls it a 1. If she sees much less than n/2 systems, she calls it a 0. And that's sort of a way of estimating the covariance if Alice and Bob both did that. And that's the technique that I'm imagining you could use, right? That generates something that looks like a secret key. Whether or not it is a secret key and what assumptions you need, I'm not sure. But Alice and Bob could do that, check that it violates the inequality, and then maybe claim something like a secret key.
I think Alex Lasek from our group has a question.
Hi, Adam.
Hi.
I wanted to ask, how do you go about generalizing this to systems that are not just pairs, independent pairs that are entangled, but are more sort of realistic, where there's more entanglement and...
Yeah, that's a good question. It's hard to imagine, it's hard to give a very general answer. Because I guess you don't want to upgrade all the way to just sort of arbitrary macroscopic systems. Or I guess that you would expect this test to break. But if you can get sort of a handle on the types of correlation, if you have some large global correlation, but you sort of understand what it looks like and can assume that it has a certain form. Like, let's say that I can assume something like bosonic statistics. Then I still don't know, but the problem sounds tractable. So you need to add that, you need to enforce that as an assumption. Just like here I said they're pairwise independent. If instead said everything is bosonic, then maybe it would be a different bound, but you could hope to get a bound with a similar flavor.
Yeah.
It's a hard question, but it's kind of a cute one. I mean, it's cute as underselling it. It's a nice one.
Thank you. And also wanted to ask how this would compare to sort of solid state correlated quantum systems like superconductivity or whatever goes on in, let's say, bilayer graphene.
Yeah.
Those are correlated.
Yeah, this is above my pay grade slightly in that I don't know a ton about bilayer graphene, but the part of the answer, at least, is to say that there the entanglement certainly isn't pairwise, but we do sort of, I think, have some understanding of how how the entanglement works, right? Like you have entanglement along a graph or something like that. So again, you sort of have this. At least if you could find the right assumption to make, sort of restriction right assumption to make to put your classical and your quantum system on equal footing, you could hope to recover a test like this. Like, you know, I guess one thing that certainly shouldn't break this test is if instead of having pairwise entanglement, you had like entanglement in triangles or something like that. I don't know how to do it, but expect this test, this sort of idea to generalize to that.
Thank you.
Welcome.
I think Alex number 2 has a question as well. Have you tuned in, Alex?
Hello. I prefer
Hello.
to call myself Alex 1. There are sufficiently many Alexes in the world to cause overflow and become a negative number. So my question is, you did say that there is an extra underlying assumption that we have to, within Alice and within Bob, make sure that each of the photons is, shall we say, decorrelated from the other photon from the same family.
Yes. Yeah.
Can we reliably detect if we haven't breached the Bell inequality? Is it because of the classical correlation that we have just failed to detect in Alice and Bob? Or if quantum mechanics is just simply wrong or something wrong in the assumptions?
Right.
Are they
right.
cases?
So the sort of real the true answer is no. You know, you could have a very sort of, I guess if you just imagine this test ultimately as giving you a number, you know, that's between 16/7 and 2√2, or actually larger. You know, if you see a number that falls below the classical limit of 16/7, it's you can't. Yeah. I mean, I guess at that, when you're that zoomed out, you know, you could, I guess. Sorry, let me say it like this: anything quantum mechanical, you could spoof with a clever enough global correlation.
Can you tell apart? Can you tell that apart? Quantum mechanics isn't working, or if it is working, it's just that we can't detect it.
So let me. Are you imagining a situation where you have a global correlation that sort of breaks your classical bound, or where you don't exceed the 2√2 bound, or where you don't hit the quantum bound?
Second case, where you don't
Yeah. I guess the answer is still no, but yes, yeah. The answer there is no, but it's yeah, no, but it's not a. I think I see where you're going with this. Tell me if this is a rephrasing that sounds reasonable. I mean, like you're saying, let's just say there was some quantum mechanics breakdown at some scale. I mean, would this test notice that? Yeah, I think. I mean, I think not. I think it would just look like you do everything right, so that you expect to hit 16/7. You expect to hit 2√2, and you don't. But that failing to hit 2√2 is a different sort of problem than not noticing global correlations. Because the worst thing global correlations can do is they can spoof quantum mechanics, right? You can think that you've seen something quantum mechanical when really it's been caused by global correlations. But if you don't see something quantum mechanical, even when you expect to, well, then you know, I mean, then your quantum mechanics is somehow broken. Whether that's because there are some global correlations in there that you didn't notice, or quantum mechanics itself had a breakdown. I mean, either of those are sort of surprising, because you can always, you should worry about global correlations making it look like quantum mechanics happened. But, you know, if something's flattening quantum mechanics, it's kind of exciting whether it's a global correlation or something else. Does that make sense?
Yeah, that answered my question.
Cool. Thanks. Yeah, thanks for the question.
Do we have any other questions from people in the audience or on the panel? I had a small question. Well, actually,
Sure.
if we have just another minute, maybe. The first one was I'm just curious about the chronology of how you came up with this, because like if I wanted to try something, I would try what you tried first with just the standard Bell test of the mean, and then that evidently didn't work, and how was it just natural to go to the covariance, and then like
Yeah.
not the most known paper, this covariance version of the Bell test either. So just how do you come up with such a thing?
Yeah. I mean, this is this might be partially a story about my my failure to do due diligence before starting research. In that, I guess this was really actually started with a sort of very experimental question, which is that Nicole had heard about a proposal to test for entanglement in biofluids, where they weren't even doing the Bell test in that proposal. They were doing sort of this first thing that I talked about, where you just notice correlations, potentially notice correlations. And so we had talked about sharpening that to a Bell test. We sort of got as far as noticing that the regular Bell test broke. And I think this sort of first order, second order moments picture was what started pushing us towards the covariance. You sort of realize that you don't care about the means, you care about the variances. That's where the fluctuations happen. So can you do something with the variances? And I had gotten some amount into trying to construct such a thing when I Googled covariance Bell inequality. I sort of realized I wanted a covariance Bell inequality, and then Googled it, and then the paper finally popped up, sort of through happy coincidence, and then everything came together quite nicely.
Okay, well that makes sense. And
I should actually say, sorry, just to advertise it, Miguel Navasquez had a work with a lot of different techniques, but similar ideas, maybe early 2010s, but I don't have the date exactly, which is also something, just while I'm talking about all of this, similar ideas are floating around back there that are kind of nice to look at. And yeah, I feel like I should advertise that paper as existing. Of course, I don't remember the name, but yeah, you can hunt it down.
Yeah. And you said you had some experimental slides. Maybe we could just
yeah.
1 minute have a look at those.
Just mindful of time. We're gonna have to end this meeting before 12:30 though. So
oh, okay.
Careful.
Yeah.
I know we could go on for another hour. This is very interesting, and this can get into extremely lengthy discussions, but we just have to be mindful of time.
Yeah, maybe even without even showing the slides, then I can just say the original sort of biomolecules, biofluids proposal. Sort of just fun to imagine just the possibility. Is there a chemical? You can imagine a chemical reaction that has, some molecule splits into two molecules that share entanglement, and then you can effectively make a measurement on these molecules by, in this proposal, seeing whether or not they bind to another molecule, which will then fluoresce or something like that. So if you started with many of these biomolecules, which all split, and you somehow, after the split, swept half of them into one test tube and half of them into another, then you have exactly this macroscopic setting that I first defined, where you've got many copies of independent systems entangled with another independent system. That's happen to have it open, the two vial tubes picture.
Well, yeah, thanks a lot, Adam. This was super interesting, a really fun and cool talk. For the part 3 master students who are attending, if you're interested in Bell tests, I really recommend reading one of the appendices from Adam's paper, which I think had an amazing description of a standard Bell test, basically.
Well, thank you.
So yeah, thanks a lot, Adam. Hugo, is it the case that we're finishing this meeting completely, or are we